Okay, so my name is Paul Robinson. I'm a co-developer at Jboss, the Red Hat. I'm a member of the Transactions team, and I also lead the Web Service Transactions project. So, what I'm going to talk to you about today is it's rooted within Web Service Transactions, but it's what we're doing is making it more applicable to other scenarios beyond web services. And essentially what I'm going to talk about is what the problems we have with ACID transactions and which scenarios aren't really appropriate for using ACID transactions. And I'll show you that you don't have to, just because you don't want to use ACID transactions, doesn't mean you have to throw transactions out altogether. There is an alternative which may be appropriate. And that's basically the work that I've been doing recently, so around these compensation-based transactions. So, okay. So the agenda. So there's quite a bit of background that I need to cover, unfortunately. So I'll briefly talk about ACID transactions and what some of the problems are around using them, and then we'll that should give you an idea of what scenarios maybe they're not appropriate in. I'll also then go on to introducing what a compensation-based transaction is, and compare them to ACID transactions, so you can see where they're similar and where they differ. And once we've got through that background, we'll jump into the meat of the talk, which is going to be covering 3 scenarios where you might find ACID transactions are not appropriate, and then I'll show how, using our technology, you can use a compensation-based transaction to hopefully solve that problem. And then at the end of the talk, I'll talk about what we've got at the moment in this API and what we've got planned for in the future. And then I'll close with some getting started links, so you can if you're interested, you can go off and try this out at home. So, okay, so ACID transactions. I guess most of you guys are familiar with it, so I won't go into too much detail of what an ACID transaction is. But essentially, it provides some strong guarantees. In particular, there's 4 guarantees really that we're looking at. We've got atomicity, which basically ensures that either the whole transaction happens or not at all. Consistency essentially makes sure that the system moves from one consistent state to another consistent state. Isolation, that ensures that one transaction can't see another transaction that's in progress, and vice versa. And then durability is just basically that once the transaction is completed, its state changes are persisted to some durable storage. Okay, so there's many positives to using ACID transactions. So I'm not going to be today. I'm not trying to say that there's probably that they're rubbish, because they're actually a good technology, but they're just not necessarily applicable for every scenario. They do provide very strong guarantees, as I just explained with the ACID properties. They are very good at tolerating certain types of failures, so they can be used in fault-tolerant scenarios. There's also, we've got quite advanced, easy-to-use APIs for using ACID transactions now. So if you're familiar with using the EJB transaction attribute or the new transactional annotation with JTA12, you'll be familiar with how easy it is just to enable a transaction, and it just all works. Everything's done under the covers for you. So that's all the good things. But on the negative side, in order to achieve an ACID transaction, we have to use this. Well, typically we use a 2-phase protocol, which relies on blocking. So at certain stages in the protocol, the resources that are involved have to lock their data, whilst other participants are making progress, and they're essentially waiting. So there's a lot of blocking can be going on. I'll talk a bit more about that later on. And due to this blocking nature, we can also reduce the throughput. So even if you've got quite a lot of power, a lot of CPU available to you, if you're waiting on some other transaction to complete, you can't make progress, and you're not going to get high utilization of those resources. It also relies on you having 2-phase aware resources, so the things that you want to involve in the transaction have to be they have to be able to participate. We need to implement the right interfaces to be able to plug into this transaction, which is fine for certain things like databases and message queues, but it's not so good for other things like printing letters and sending emails and dispatching packages and things. It also encourages a lot of tight coupling. So again, I'll talk about that in later slides, but essentially we get kind of tight coupling between the client and the database, and also the transaction manager in the database, which may be fine if everything's operating in the same business domain, but it's not if these parties are in different business domains. We don't want this tight coupling right the way through. Again, I'll talk about that a little bit more with some diagrams. So, okay, so after you've kind of looked at the pros and cons, you might be thinking, well, you know, for my situation, ACID transactions, they're not going to work. And that's quite common, we hear this. However, just because you can't use ACID transactions doesn't mean that you should give up on transactions altogether. The kind of ACID transactions are not the be-all end-all when it comes to transactions. There are other protocols available, they're just the most popular. Okay, so we've got so there's kind of an umbrella term that's used to define so a group of transaction protocols that relax one or more of these ACID properties. So this is called extended transactions. So there's a number of these protocols around, and the research has been going on for 10, 20 years. But essentially the idea is that if you look at this spectrum of guarantees, imagine if you don't have transactions at all, you have very few guarantees, so no transactions, very few. Then as you move over to ACID transactions, you've got very strong guarantees at this end of the spectrum. But kind of if these guarantees are too much and they're not working in your application, you don't have to drop right back to no transaction. You can pick a transaction protocol on this spectrum, an extended transaction model that fits your needs, and maybe you relax the properties, the ACID properties that you don't actually need in your application. I'm going to be talking about compensation-based transactions. So in Narayana, which is the JBoss Transactions project, we've actually got support for 3 different extended transaction models. So we've got top-level transactions, nested top-level transactions, and compensating transactions. So I'm not going to talk about the other 2 today, it's just about the compensating ones. So our implementation is based on sagas, which is some academic research from 1987, so it's quite an old idea, but we're kind of thinking that it's not really been that widely applicable in the past, but now with in the current climate, we're hoping now's kind of the time when it's becoming more useful. So what's the difference then between an ACID transaction and a compensation-based transaction? So essentially with an ACID transaction we have 2 phases, if using 2-phase commit. In either when the business logic is invoked or during the first phase, we require locks on the data. We prepare the transaction. And then in the second phase, we either commit the transaction, which releases the locks and makes the changes happen, or we roll it back. Here we release the locks and discard the changes. And we have locking between these 2 phases. However, with a compensation-based transaction, it's a bit different. So here, in the first phase or during the business logic phase, the changes are made immediately and committed and visible outside the transaction. And then in the final phase, those changes are either confirmed or just left because they were what we wanted, or if the transaction needs to be cancelled or undone, then a compensation handler is invoked to undo that work. Okay, so you're probably all thinking, so hang on, what effect does this have on my consistency and my isolation? So you're probably thinking this looks a bit dubious, it kind of looks like we haven't got any guarantees at all now. So yes, it can have an effect on your isolation and your consistency. So as I was saying before, you do need to, if you're not going to have the full ACID properties, you want to get some of the benefits, you do need to relax some of these properties. So isolation is affected because essentially we're talking about committing the work early, so other transactions can see the progress of the currently running transaction. And also consistency can be affected because another transaction can see in progress work of the not yet completely finished transaction. And that transaction may later be compensated and undone, in which case your application could have seen something that was in progress. So consistency essentially is relaxed as well to eventual consistency. So yes, it maybe does look a bit dubious, but as I'll show you later on, there is actually patterns you can follow that actually, in some circumstances, still withholds isolation and consistency. And in other cases, it reduces it in such a way that it might not be a problem for your application. But again, it's not a one-size-fits-all solution. So, okay, so let's take a look at roughly how an ACID transaction works and how the locking happens. So, okay, so the client, first of all, begins the transaction by calling begin on the transaction manager. That starts a new transaction. It then invokes some business logic or some service in the scope of that transaction, and that will then potentially maybe update the database or send a JMS message or something. Now, if we're using pessimistic locking, the database will lock the records involved in that update here. And then that will return back to the client. So the client can now go and make update, invoke other services, invoke other business logic, or do its own internal stuff, or just twiddle its thumbs, or whatever it likes to do. And then finally it can decide to commit the transaction. And then this is where the two-phase commit protocol begins. So the transaction manager will then drive all the resources that are enlisted through the two-phase commit. So we'll start by preparing the database. So if we were using optimistic locking, this is the point when the database will check to see if the change is still valid, so nothing's changed in between. And if it hasn't changed, then it will require locks at that point, but it's still acquiring locks. That prepare will then return, basically saying whether it's capable of, whether it's going to commit to, finish the transaction successfully. Transaction manager can then go and prepare all the other resources, again taking time, all the while this database manager is having to hold on to these locks, and it can't release those locks, which shouldn't release these locks anyway, until it's told by the transaction manager to do so. It can make a heuristic decision, but again that's bad, because you can end up with an inconsistent outcome. And finally, the transaction manager tells the database to commit, and at that point it can release its locks and persist its changes. And again, I've got a little clock here showing that there's obviously a time between when the transaction manager then goes and commits the other resources. Okay, so essentially the problem we have is that the database is tightly coupled with the client and the transaction manager, and it has to keep hold of its locks until it's told to do so by some external party. So this is where where the tight coupling comes in that I was referring to. So once the database has got its locks held here, the client can then dither around till either the transaction times out, or it tells the transaction manager that it would like it to be committed. And again, we're also restricted by the time it takes for the transaction manager to invoke these here. So this is fine if everything's within the same organisation, but it's not going to be acceptable if your database and your service maybe is running on Amazon, is Amazon, and the client is some third-party service that's kind of mashing up something in Amazon and something in some other company. Okay, so how do compensation-based transactions work? So similarly to the ACID transaction, the client begins the transaction by telling the transaction manager to begin a new one. It then invokes the service as before to make the update. But with a compensation-based transaction, what we do is we begin a new JTA transaction here. So we've begun a compensating transaction here, and then we can begin a JTA transaction here. So this is if we're using a JTA resource. If it's a XA resource, so something that can participate in a JTA transaction. Otherwise, we can't do this, but I'll talk about that a little bit later. So yeah, so we begin a new JTA transaction here. We make the update to the database, and then the business logic tells the transaction manager it's finished. But at this point, the transaction manager commits that transaction, and at the same time, it writes to the log a compensation handler. So that's some business logic that can be invoked sometime in the future to undo that work. So it's reliable because we commit the transaction and write the compensation handler to the log at the same time. So the important thing here is that by the time this service returns control to the client, the transaction has been committed and there is no locks being held on the data in the database at that point. So the database is freed up. And then the client can then go and invoke its other services, take as long as it wants to do so. It's not a problem because the database isn't waiting for it to respond. It can be doing other things with that data in the meantime. So then finally the client can then request either close or cancel, so this is kind of the equivalent of commit or rollback on the transaction. And then that will be then passed on to these handlers that we talked about before. So if we need to cancel the transaction, then the compensation handler would be invoked here, which again can begin a new transaction that can go and update the database to undo or take some compensation behaviour to handle what was done in this phase. So maybe where here we might be making a booking and here we might be cancelling that booking, or here we might be marking the booking as pending and here we might be cancelling the booking. But we can also register a confirmation handler, which is essentially a piece of code that will be invoked if the transaction was successful. So we're in a situation where we can, once the work's been done here and this is returned, we reliably, the application is reliably told whether the transaction completed successfully or not. It will definitely get one or the other. Even if there's a failure, it will still get told the outcome of the transaction. But importantly, it didn't need to hold its locks between these phases. And also we've got rid of this tight coupling as well. So we've now got this, the database is only ever interacted through the service. So the transaction manager and the client talk directly to this service logic. So we've decoupled the back end from the client and the transaction manager. Okay, so, and again, as I say here, these changes are visible. However, I'm going to show one of the examples how it's possible for that not to actually matter. It would depend on your application scenario, but potentially it's not actually a problem that those changes are visible.
That's a question, sorry.
Yeah, go for it.
So the compensation handler, is that something the service layer programmer is going to have to write, or is that automated?
No, it's something you have to write. There's been some research on trying to automate it, but the thing is, you could kind of you could go and undo what was done in the first phase by kind of monitoring what was done. But I think generally the problem is that you kind of have to, you might have to go and take some other action to see what's been affected by that. So it is very application specific, and it does put burden on the application developer.
So I guess if your action was subscribing to something, then it's not just removing subscription, but these news items have been distributed to you as a result. They've got to be.
Yeah, potentially, yeah. So it can be a bit of a burden, but I think what we're talking about here is we're talking about keeping strong guarantees whilst raising your throughput of your application. So it's you're in a situation where you're willing to put this effort in. It's not something that you would necessarily just use off the cuff. When the handler's invoked, is there a way of passing another handler to it? Or?
Yeah, I mean, if the handler also starts a transaction, right?
Yes.
It is conceivable that that also fails.
Okay, so I think the question is that what happens if one of the handlers starts another compensating transaction within itself? Is that the question? Yeah, so that's not allowed. It's the same with JTA. You can't start within like the commit or the rollback method. You can't start a new transaction in there. However, you can start and it's encouraged. You can start a JTA transaction. So a compensation-based transaction can be made up of two JTA transactions, one to do the work and then one to either confirm it or compensate that work. And because you're using a transaction at both levels and the transaction manager is involved in both transactions, we can tie them together reliably and we can make sure the recovery happens properly. So it is a trade-off what we're talking here. So what it boils down to is you're trading off. Sorry, before I go into that, did I answer your question?
Yeah.
Okay, great. So what we're trading off here is in the ACID case, we have one transaction, one JTA transaction where you're holding locks across this gap here, and you have fewer disk writes, and you don't have as much burden on the application developer. For something here where you don't have to hold resources over this gap here, but you do have to write a compensation handler, and you do have more disk writes. But as we were talking before, if you're using an ACID transaction and you're waiting on things to happen, you could potentially have a lot of hardware available, but because your transactions are all blocking and waiting on each other, you're not getting very much utilization out of it. So you'll probably end up using more CPU cycles with this approach, but it will scale to much more potentially.
I'm just wondering, is there anything you have to be particularly aware of in the situation where your initially committed data is then changed by a subsequent operation if you then find yourself needing to invoke compensation?
So I think that's, yeah, so the question is, do you need to be careful to make it, so do you need to take into account the fact that if once that the change has been committed, if another transaction then goes and reads that state,
it's not so much if it reads it,
or if it makes a change. Yeah, something happens based on that change, which is then compensated. So yes, basically that is a problem, that the application, it's a burden of the application, I'm afraid. So they need to be able to, in the compensation handler, it would need to somehow be able to find out what had been impacted by that change.
Okay.
So it would kind of depend on you. So this might not be applicable if you've got a kind of a write-heavy situation, and there's lots of things are happening based on the work that you're doing, then it might not be applicable in that situation.
Okay. So it's a use case type thing. So if you're in a scenario of booking where cancellation is the compensation, if you change, if you modify the booking in some respect, you can still compensate by cancelling.
Yeah, so
that's okay.
It is because I think what I would do in that situation is I'll just mark the booking as pending. So I'll show that in an example later on, but in the business logic phase you mark the booking as pending, so that then in this phase here, when the changes are visible, if you go and look at it, you say, oh, I've got maybe 20 bookings and 5 pending bookings. So you can then you can reason about it. So I think one of the important things to think about here is the fact that we're still holding locks, but we're moving them up to the application level. So you could imagine having a hotel or a flight is a good example. You've got a plane with 100 seats on it. You might have 90 booked, and then you've got 20 people come along and try to, what do? Do you just mark the first 10 as pending, or do you overbook? The flight companies, they overbook. So what they're doing there is they're moving the locks up to the application level, so they're locking individual seats. But because it's in the application level, they can reason about it. So they can make the decision that, okay, I'm going to actually lock 110 seats, even though I know I haven't got them, because it's quite likely that 10 will cancel anyway. And the worst thing that's going to happen is I'm going to have to upgrade 10 people. I'm going to have to pay 10 people off to go on the next flight. If I don't do that, the worst case scenario is I've lost the money for 10 seats, which is a lot of money. So we're still locking things, but it's at the application level, which means that we can reason about it, rather than being at the database level where we can't.
So you end up with some more complex state transitions and things like that, more intermediate state.
Yeah. So it is more complex from the application writer's point of view, and it may turn out to be too complex for your situation. But as we were saying before, you're talking about, you wanting to keep the guarantees while keeping your throughput high. So we're talking about quite high-end applications potentially here. Or you might have quite a simple application, in which case it wouldn't necessarily be a problem to do this. Which the kind of the examples I'll show later are quite simple, so you'll see it's not necessarily that much of a hassle. Okay, so do people kind of get the idea of the difference between compensation-based and ACID transaction? So we'll now, shortly come on to the examples. So prior to this work that I'm talking about today, we did have some support for compensating transactions in Narayana. So Narayana is the JBoss Transactions project. So we had an implementation of WS Business Activity. So this is an Oasis web service standard. But because it's a web service standard, all it really standardizes on is the message format, so what the messages should look like on the wire, the SOAP messages, and the state machine that applies to each end that's sending the messages. So the idea being, if you receive this message, then you move to this state and send this message. It doesn't talk about the API, there's no binding like JTA, there's no binding to the application, and because it's SOAP, it's kind of independent of any implementation technology like Java or .NET. So we're kind of on your own if you want to put an API on this. So the problems we've had with this is that it's very specific to web services, so our implementation is anyway, and the other ones I've seen now as well. Also, the API is very low level. It kind of deals with, it's very tied to the web services standards, so it's quite difficult to, if you want to change your code to work with a different technology, it's quite difficult to do that. And it's also just hard work for the application developer to write. So, so basically, to solve this problem, we've developed this Compensations API. So this is kind of JTA-like API, so it provides the Java binding to using the compensations-based transactions. And we still use JBoss Business Activity under the covers, and we use that for distributing. So you can write a distributed compensation-based transaction, and the distribution is done via JBoss Business Activity. But there's nothing that's tying it to web services. You could, if we create a different transport, which we've kind of got plans to do for REST, you can plug that in, and your application wouldn't change, apart from it would need to talk to REST endpoints rather than web service endpoints, but that's kind of to be expected. The focus at the moment is an application API. JTA covers the application server and the resource manager as well. We've got no immediate plans to do anything around the application server. We are thinking about resource managers, so we're kind of thinking about what support needs to be there for NoSQL databases. But we haven't really given that much thought yet, but we hopefully will be doing soon. It interops with JTA 1.2, so as I was saying before, you can compose a compensation-based transaction out of multiple ACID transactions using JTA. So it supports the new JTA 1.2 annotations, which Narayana now supports. We were certified quite recently with JTA 1.2. I think we're acknowledged as being compliant, I think is the term I'm supposed to use. So, yeah, and it's transport neutral, as I was saying before. So that's kind of the main requirements we have for this API, and it's a lot easier to use. That was a very key requirement. Okay, so on to the examples. So basically I'm going to go through like 3 scenarios where you wouldn't want to use an ACID transaction, and I'll sort of show with code how a compensation-based transaction could fit that scenario. So the first one is a non-transactional resource. So here we kind of, well, to explain what a non-transactional resource is, I'll talk about what a transactional one is. So essentially a transactional resource is one that can participate in a 2-phase commit protocol. So you need to be able to prepare that resource and then later tell it to commit or roll back. So we're talking here like relational databases and message queues. A non-transactional resource, here we're talking about things that can't participate in 2-phase protocol. So we're talking things like a printer or an email, sending an email or sending a letter somehow. You know, these are things that they don't really fit into the kind of the prepare and then commit rollback scenario. So yeah, if you want to include one or more of these types of resources in your transaction, then compensation-based transaction could be an option. So I'm going to show a code example now. So here we've got an e-commerce site that's selling books. What it's going to coordinate is the update of a database, which might be in an XA transaction, so to a relational database, or it could be updating a NoSQL database, which isn't an XA resource, and also dispatching of a package. So that's kind of something that really isn't 2-phase capable. So let's have a look at the service first. So this service class is the thing that's invoked to buy the book. So maybe the web interface invokes this method, I don't know. So we've got a buy book method, and what that method does is it calls the package dispatcher to dispatch the item. It also updates the database, and we want to coordinate these two invocations inside a compensation-based transaction. So all we do is we annotate that method as @compensatable. This is very similar to having @transactional or @transaction attribute in the JTA world. And what it essentially does is it says that this method needs to run inside a compensation-based transaction. If there's one running, then great, use it. If there isn't, create a new one. And by default, if there's a runtime exception thrown, then it will cause that transaction to be undone. That annotation can be customized, so different types of exceptions can or may not cancel it, but that's not covered in this example. Okay, and then we're just injecting the package dispatcher, so that's not really too relevant. Okay, so let's have a look at the result, the non-transactional result. So this is the package dispatcher. So this dispatch method, this is the method this is the actual business logic that we're going to do inside the compensation-based transaction, and it's something that in the future will need to be compensated if the transaction as a whole is undone. So what we do is we annotate it with txcompensate, and we provide a class name, and this is the handler doing the compensation. So this is the compensation handler. So it says once this method is completed, if the transaction in the future needs to be undone, invoke an instance of this class. Now, that's all well and good, but when that instance is invoked, it needs to know something about the transaction that we're compensating. Because it's like, recall package, what package? I don't know what package to recall. So we have this injection point here. So all the data is an application-specific POJO in this case, and it's simply injected into the class. And then we can, inside the dispatch method, we can set some data on it. And this data is then made available later to the compensation handler so that it can undo it. So it knows what address to recall the package from and what item it's expecting to be able to recall.
Is that transaction scope is then the order data? The checked is that transaction scope?
That's the next slide. Yes. So are you familiar with the JTA 1.2 transaction scope? It's basically the same as that. So yes. So we've got this compensation scoped annotation that we place on the implementation of the order data, and that says that when you inject when an instance of order data is injected, make sure that instance is tied to the transaction, and any time you invoke a method, a class with that injection point within that particular transaction, always have that same one. And if it gets invoked in a different transaction, then you get a different instance of it. And then when the transaction finishes, that instance is discarded, it's automatically garbage collected. And so yeah, JTA has a similar thing. You can have a transaction scoped, which means that you can do the same thing with a JTA transaction, and this is basically exactly the same, but for a compensation-based transaction. So we've been very careful to try and align the two specifications, so that if you're familiar with JTA, especially the new stuff, then hopefully you'll be familiar with what's going on here. So does that answer your question? Excellent.
Is that a CDI scope or any kind of integration?
Yeah. So this is all implemented in CDI. So if we go back, so for the recording, the question was, is that a CDI scope? So the answer is yes, it is a CDI scope. And the txcompensate annotation is a CDI interceptor, as is the compensatable. So in theory, this should all work in any CDI container. But at the moment, it just works in Wildfly. So JBoss 8, AS8, which has been in Wildfly. So that's the compensation scope. So here we've got the compensation handler. So we call it recall package because it's going to somehow go and recall that package for us. We have to implement an interface called compensation handler, which basically means we have to implement a compensate method, and then we somehow recall that package. And when we recall the package, we can then refer back to the information that was in the order data to find out, what package it was and where it was sent to. And the important thing is as well is that this compensation handler could be invoked after a failure. So if the server crashes and the package has been sent but the transaction didn't finish, then the transaction manager might decide to cancel the whole transaction. in which case it'll be fine because this order data here, because it was compensation scoped, it was serialized to disk at the point when the transaction was logged, as was the compensation handler class. So that at recovery time, we can just create an instance of the class, pipe in the inject the data, and then invoke the method, and it will just undo the work. Okay, so simple example. Everyone follow that? So clearly there's kind of windows of failure in there. You know, if you dispatch the package before you return, then you're going to have a problem because you don't know whether you've actually dispatched the package or not. But that's kind of the nature of using resources that are not transactional. So, but we've reduced the window to make it quite small. So it's kind of something we just have to accept in this case. But in the next example, there isn't any windows. This is kind of getting a bit more complicated now. So here we've got two examples in one, I think here. So we're talking about transactions that are distributed. So by distributed transaction, I mean kind of like we've got some logic that is on one server, then we'll invoke another service somewhere else that will maybe update a database, and then maybe invoke another service somewhere else that maybe sends a JMS message or something. So the transaction is distributed over all these servers. It's cross-domain as well, so we're including different business organisations here. So, you know, maybe the client might be some sort of travel agent, and then the services that we're invoking may be different companies. So we want to flow the transaction between these different domains. Okay, so in this scenario where we're distributed, the application is distributed, so the chances of failure is increased. The more servers you have involved, the more chance something's going to go wrong. So it makes sense that you would want to use transactions to tolerate these failures. But because we're distributed, the latency is now increased. And if we're distributed over the internet, it's even higher. So these transactions are going to take potentially a long time to run. And because we're in an ACID transaction, you've got these locking windows, that's going to increase more, which means your throughput is going to go down. So, you know, maybe you're thinking now, ACID transactions are not really going to work for this scenario. Also, if you're in a cross-business domain scenario, you really want loose coupling. You don't want the client to be able to dictate when your database at the back end releases its locks. Neither do you want the transaction manager to do so. So, and ACID transactions are inherently tightly coupled, so you know, maybe that's not good either. However, I'm going to show here how compensation-based transactions could be used in this scenario. So, I've kind of hinted at this before, but the code example I'm going to cover is of a travel agent. So, what we're going to coordinate is the booking of a taxi and the booking of a hotel. So these two services are offered by different companies. They're offering a web service over the internet for us to invoke to do this booking. And we're using WSBA, so WS Business Activity, as a way of distributing the transaction. Okay, so this is what the client looks like. So kind of similar to the last example. So we've got a method that's annotated as compensatable. So that's going to begin a new compensation-based transaction if one doesn't exist, or it's going to use an existing one. Now, something I didn't mention in the previous example is that you can also pass in a policy, so you can say it's mandatory. So, for example, you know, like you can in the JTA world. So, default is supports, but we could have things like mandatory, which means it'll fail if there isn't a compensation-based transaction in place, or required, and so on. So then, okay, so we've got this method invoked. We know that there'll be a compensation-based transaction present at this point. We then look up the hotel and taxi web service port. So here we're kind of just getting hold of our stubs for the services. Nothing too interesting, all very web service specific, so I'm not going to show that here. And then we call make booking on each one. Now I'm going to book a double room on the hotel with my email address, and then I'm going to book a taxi from Newcastle with my email address as well. Now, the transaction context is automatically propagated by the middleware, so all you need to do is just invoke the service. it'll automatically get the transaction context, put it on the stored message, and pop it out the other end. And it will make sure that there's a compensation-based transaction there ready when your actual service is invoked. Okay, so let's have a look at one of the services. Now, there is some colour coding on here, but the projector doesn't seem to be favouring black and white. So the slightly green ones are our annotations. The other ones are like JTA or web service ones. So what we've got here is kind of a regular JBuG web service. Now we've got a make booking method here. So that make booking takes the information about the booking and then updates the database within the JTA transaction. So how do we make all this happen? So, okay, so we've got a JTA transactional annotation here. So that's saying we require a new JTA transaction. So that'll make sure, that annotation will make sure that this method here is invoked in a JTA transaction. And if the method completes successfully, it'll commit that JTA transaction. We also have this compensatable mandatory. So that's basically saying that there has to be a compensation-based transaction present when you invoke this method. And as I was saying before, when the service is invoked, if there was a context available, it will be propagated, and the middleware will make sure that that compensation-based transaction is available. So that's kind of just like a safety net to make sure that happens. And yeah, because it's a third party that's invoking this, it's, you know, we can't. It's a way of kind of guaranteeing that they've actually done what they're supposed to do. And then we have two other, the TX compensate annotation, which you may be familiar with. So that's specifies what to do in order to cancel the booking. And then we have this confirm one. So this is kind of the counterpart to compensate. So if the transaction is successful, we get notified that it was successful. So exactly one of these two will be invoked, even in the case of failure. So this is the confirmation handler. So we'll look at those soon. And then we've got the web method, which is just a JBuG thing. Okay, so makes sense? Yeah, quite simple.
Who takes care of compensating for the database update?
So the question was, who takes care of compensating the database update? So that's the compensation handler. Is a cancelled booking will need to do that. So here, so what's happening here is you're updating the database and marking the booking as pending. So what you're doing, I probably should have explained this, but I forgot. You're creating a new record in the database, presumably, saying I've got a booking on this hotel, so a room, and the booking is in the state pending. And you've committed that to the database. So at that point, it's not, the booking's not made, but the hotel company knows that somebody's potentially going to want that room.
So compensation handlers in general are not resource specific, they are specific to the operation that will compensate.
Absolutely, they're application specific. So they do whatever the application needs to do to be able to undo that work. So in the previous example, they somehow recall the package. I don't know exactly how you recall packages. Maybe you send an email to somebody and tell them to. I don't know how you recall a package, but that's kind of the domain of the application to know that. So in this, it's kind of simpler when we're dealing with databases and things. It's a lot easier because we can because we're still dealing in the domain of transactions. It's when we go outside of that domain, dealing with things like these, things like dispatching packages and sending emails. That's when it's a little bit trickier to get right.
Let's say you bring together 5 transactional resources in one service method. Your compensation handler will need to take care of those 5 transactional resources and make it unbound.
Yes, yeah. But if you're using, I don't know, maybe if you're updating, like I said, database and something else, then you'll be listing the same JTA transaction. So that will make sure that they all happen. But then you need the compensate needs to be the counterpart of what you did. So in that case, you need to kind of update all those same things, but in another JTA transaction, which ensures that they're all grouped together. So it should be safe. So I guess the idea is that if there's a problem when you try to update the database, if there's some sort of runtime problem, that means you can't update the database, and that will cause an exception to be thrown, which will then potentially cause the whole compensating transaction to be undone. So now the confirmation handler. So remember, in the business logic, we just updated the database and marked the booking as pending. That's now visible for everybody to see, which is fine, because they know it's pending. If we'd marked it as booked, then we might have a problem, because other applications are seeing a kind of what the transaction would be like if it finished successfully, but we know it might not. So that's why we marked it as pending. And that's why it's not necessarily a problem that other transactions have seen this kind of in progress state, because we can kind of reason about it. But in the confirmation handler, so this is at the end of the transaction, all the other parties involved have been successful. So now it goes and the transaction manager goes and notifies the services that it was successful, and it invokes this confirmation handler. It's similar to the compensation handler in that it implements an interface, which means it has to implement this confirm method. And again, you can inject the data so you know which thing you're confirming. And in this example, what we do is we do it inside another JTA transaction. So we've got this transactional annotation here, and we're then going and updating the database, and we're changing the booking from pending to confirmed. And again, that's reliable, because this method will be invoked over and over until it's successful. So this is, what we basically mean is we're getting at least one semantic, so the application has to be able to handle that. Which in this case would be fine, because you would check that the booking was in state. If it's in pending, change it to confirmed. If it's already confirmed, then do nothing. Okay, so the key thing I want to get across there is the fact that we've relaxed the isolation and the consistency, but from the transactions point of view, but the application hasn't suffered from it. So does that kind of make sense? Okay. So we've kind of been able to work around the deficiency in the protocol. We've worked around the relaxed guarantee, so we're getting the benefits of the protocol without suffering from the negative side. Okay, and the compensation handler is very similar. It does the same as the confirmation handler, but instead of marking the booking as confirmed, it marks it either as cancelled or maybe just deletes it, whatever. It doesn't really matter. It kind of updates the database again inside another transaction. Okay, I think that's okay. So that's the end of that example. Now the third and final example: long-lived transactions. So ACID transactions, as we said, are all or nothing. Whether all the changes take place, and if there's a problem, then we undo them or we roll them all back, and we're back to square one. And that's fine for a short-lived transaction, a few seconds at the most, It doesn't really matter that you've got to retry the work, because you haven't really lost very much. But if we're talking about a long-lived transaction, so something that takes many seconds, minutes, or even days, we don't necessarily want to undo all the good stuff we did, just because something went wrong that wasn't actually that important. Maybe we can find an alternative for that thing that went wrong. So compensation-based transactions allow us to still make progress and therefore support these kind of long-lived transactions. So essentially what we do is we split the work into a number of short-lived transactions, and then if one of those fails, we don't have to compensate all the ones that have happened before. We can kind of find an alternative. And then if that one works, we can still make progress with the transaction. And if there is no alternative, then fair enough, maybe we do have to go back to square one, in which case we've got the compensation handler, so we can actually do that, reverting back to the start. Okay, so I'm going to build on the travel agent example here. So here we've got a hotel and 2 taxis services. So what we really want is, we really want that hotel, and ideally, we want a taxi as well. We want to be able to get to the hotel. But hotel bookings, once you've got the booking, you don't necessarily want to lose it, because it might not be there when you try to make that booking again. So the hotel booking is very important, but if a taxi fails because they're fully booked, for example, you don't want to, you might want to find an alternative. And if you've got 2 taxis, then try the next one. If that fails, then maybe then we cancel the hotel and think about going somewhere else. So the code is very similar to the previous example. So I'm just going to show you the client side. So this is the thing that's invoking the services, so like the travel agent. So again, we've got this compensatable annotation, which says I want to invoke this method within a compensation-based transaction. We invoke the make booking service. Sorry, we invoke the hotel service, make the booking. Now if that fails and throws a runtime exception, then the compensation-based transaction will be cancelled. Nothing will be compensated because that one failed and there's nothing to compensate. And then we're back to square one with nothing changed. We then invoke the taxi service booking method. Now, if that one fails, it can choose not to. We can specify what exceptions should cancel the whole transactions and which ones should be handleable by the level above. So in this case, we've said that we want the booking exception to be handleable at this level. So because the make booking and the taxi service threw this exception, it knew that it failed. So it is responsible for making sure it doesn't leave itself in an inconsistent state. So it essentially resigns from the transaction. So it didn't work, and I'm resigning from the transaction. So at this point, we know that we can either invoke an alternative or we can just fail a transaction. So in this case, we're going to try an alternative. So here we try the second service here, and we call make booking on the second service. And if that succeeds, then great. We've got the hotel and the second taxi, but not the first taxi. If that fails, then we let the exception percolate through, and then it'll be caught by the compensatable interceptor, or this annotation, which will then undo the transaction, and it will compensate the hotel to cause the booking to be cancelled. Okay, so essentially what we can do here is we can compose lots of different services, and if some of them fail, we can try alternatives, or we can throw the exception up and have the whole thing failed. So does that make sense? Okay, so that was the last example. So what do we have today? So we've got kind of an early version of the API which covers what I've shown you today. So we've got the compensatable annotation working with the different policies on, having the requires new and the requires and so on. We've got the compensation scoped injection, the scope, CDI scope working. And we've also got Longlived Transactions working, so you can do what we did in the last example. We've got distribution working over web services, WSBA, and it is as kind of as seamless as what you've seen today. We've also got quick starts. So the quick starts, basically, there's two in particular. There's one that is practically the same as the first example, and then a second one which is kind of a hybrid of the second and third example, which kind of shows both examples in one travel agent example. They're available. I'll show a link at the end. I've also got a series of blog posts which was referenced on the abstract for this talk today. So what I did was I presented this talk at a conference in JBUG in Boston, and before I wrote the slides, I prepared a series of blog posts to kind of get my ideas clear, and it also meant that the team could review the work. And then, in a lot more formal way, it's a lot easier for them to review a series of blog posts than it was for them to review my slides, because they don't know what I'm going to say. I might talk a lot of rubbish, and they can't call me up on it. So it was a good way of kind of formalising my thoughts, and it also meant that the community gets a series of blog posts, and it's kind of that, along with the quick start, is kind of the only documentation we've got at the moment. So go and read that, but it's basically covering what I've talked about today. It's available now in M5, M4 and Ariana, so that's the version of transactions that it's in, and that's in Wildfly 8 Alpha 4, which is, if you go to the wildfly.org, I guess, you can go and download the binary, it'll be in there, and you can run out quick starts and they'll just work with that version of Wildfly, so it's pretty simple. And the great thing we do about our quick starts is that we test them. So they're all testable quick starts. So whenever we make any changes to our code in the transaction service, all our quick starts get run to make sure that they still work with the code. And when we release the transactions code, we release the same version of the quick starts. so that you know that if you get the version of the transaction manager and marry it up to the same version of the quick starts, you know they're going to work together, and we've tested them. And if you go and get the latest version of the transaction manager, if you're feeling adventurous, and the latest version of the quick starts, you know they'll work because we tested them together when we updated the code. And we also use it because the quick starts are the way we see the users using it. So we want to make sure that works. We don't want to make sure a load of low-level unit tests work. So we want to make sure that works as well, but we really want what the users do to work. So it's very important to us. What have we got planned in the future? So it's quite simplistic, the API at the moment. There's certain things that you kind of have to work around a bit if it's an application developer. But we want to be, we could go and implement that now, but we'd rather be feedback driven. So if we don't get any feedback, we assume no one's using it, so there's no point in improving it. Or if we get lots of feedback, then at least we can focus our efforts where it matters. So that's kind of what I'm doing at the moment, is I'm trying to get feedback. We're also looking for kind of use cases where this technology is useful, trying to find early adopters. I talked about recovery a lot today, but we don't actually support recovery in 2 places at the moment. So the compensation scoped, I said it, in an ideal world it'd be persisted to disk, so that at recovery time it can pull the information out when the compensation handler or the confirmation handler is invoked. That wiring isn't done at the moment. It's not a lot of work, we know how to do it, we just haven't had the engineering time yet to do it. But once people are using this technology and they start to want to use it in reliable situations, then we'll certainly implement it at that point. Also the JTA interop, so your business logic can invoke a JTA transaction, as can your compensation and your confirmation handlers. And I said that they were kind of wired together, so at the moment the wiring isn't quite there, so if there's a small failure window, if you have a failure just after the JTA transaction commits, but before the transaction log's written for the compensation transaction, then you can get in an inconsistent state. So we know how to solve the problem, we just haven't had the engineering time to do that yet. But it is something we're going to do once we've got the kind of the demand for it. EJB support, so that's really just being able to apply these annotations on EJBs as well as kind of CDI managed beans. So I think that kind of would probably work anyway, but if it isn't tested, it doesn't work, so I'm not really willing to say that it would work. Specification, it would be nice to get this standardised, but it's not really at that stage yet. We need people using it, we need other companies, other vendors interested in being involved with it. So kind of what we're talking about this stage is more just formalisation of the API so that people can discuss it and point out where the flaws are and so on. So really it's more sort of precise documentation, what I mean there. Talked a lot about throughput, saying that in theory you could get a lot higher throughput with this technology. I'd like to do a case study that shows, if you use ACID transactions, this is your throughput. With compensation based, you can get much more throughput. That's something we'd love to do in the future and feel that might be a good way of driving people to use this technology. 2 PC participants, so you don't have to be either, all the participants don't have to be in the compensations world. Maybe we can have a database, a message queue, a NoSQL database, sending a letter or something, or they all be involved in the same transaction. Maybe you have some participants that have this extended locking window and others that don't. So you can kind of pick and choose what you want. And then there's NoSQL resource manager integration. So this is something that we kind of want to look at in the near future, specifically around MongoDB. So kind of showing how we can use compensating transactions as a way of providing reliability to MongoDB. Again, it's not something I've spent a lot of time on, so you can ask me questions, but I won't necessarily be able to give you a well thought out answer, I'm afraid, but I would love to spend some time on it. We picked MongoDB initially just because it's got a massive community, but the idea would be that what we're talking about there could apply to other databases too. Okay, so last slide. Getting started. So we've got a reasonable amount of collateral. So the quick start's a great place to start. They basically just give you a working example that you can build on. Giving you the link to all our quick starts. So you'll find them under there. They're currently under the XDS project, but I think they're going to be moved under a project called, sorry, a folder called Compensations or something like that. So you might have to have a little poke around, but the README should point you in the direction, and the routes are there. That should always be current. Feedback, we're always looking for feedback. So the Transactions Forum is a great place to come and discuss ideas with us. And if you want to use technology but you're not sure how to use it in your scenario, or you found a problem with it, or you think it's not going to work for you for a particular reason, then come and tell us about it. Jira, all our issues, tracks on Jira, you can take a look there. Internally it's called TX Framework, because that was kind of like I guess it's like the internal working project name it had originally, but it's kind of evolved away from that, but we're still using that tag in Jira. The blog, subscribe to our blog. We have we post reasonably regularly on general transactions topics, but I try to talk, say a bit about this technology on there if I can. And of course, contact me directly, follow me on Twitter or send me an email. So you're saying that when we have support for recovery of the compensation scoped data, you're saying when is it actually persisted?
Yeah.
So it's persisted so when the transaction manager kind of gets to a point of no return, where it kind of has to commit, either has to confirm or compensate the transaction. It doesn't go into that stage until it's written a transaction log. So if the transaction log isn't there, then you wouldn't do the work, or you roll it back. But if it's there, then it can go one way or the other. So at that point, when the transaction manager logs its intentions, what it's going to do, at that point it will log the compensation handler class, which it does at the moment, and it will also go and look at the injected data and squirrel that way. And that's the thing that's not done at the moment, but we know how to do it. So we've got a point here where the application logic, it will, at the end of when the business logic is invoked, it notifies the, it's kind of, this diagram's not great, but it notifies the transaction manager that it's completed. So it says, I've done my work. At that point, the transaction manager finds out the compensation handler from looking at the annotation and stores that away in the log with the facts along with this participant. Essentially this is registered as a participant, you see. So it stores away the participant information here along with ideally along with the data that was injected. So then if the transaction is later needs to be undone for whatever reason, then it can go and look in its log or in memory if it hasn't failed, and look for all the completed work and compensate that work. So it's not until the complete has been finished, so this complete comes in, and then the transaction manager writes the log, and then this returns. So you don't really see this because the middleware does all this for you.
Yeah.
So as a service implementer, you'll update your database inside the JTA transaction, this method will return. At that point, the middleware takes over, and then it will. At that point, you'll prepare the. This is where it gets tricky. I think you want to know the specifics about how we tie up the.
Well, I think because that's the next bit I was thinking. So what happens if you fail before that point? You've done things that are going to need compensation. So say you've booked your hotel, and then you start writing to your database for your. You've got a level database. You keep track of your travel plans.
Yeah.
You start to do that writing, you fail.
So in the same transaction here as the.
I suppose it is.
So then that'll be fine because you'll begin a JTA transaction here. You'll update your local database in that transaction, and then this second database that you were talking about.
Well, think about that. So the hotel booking, you're going out of the web to some other company. So you say you start off by doing that.
So that's the client's invoking. So this invoke here is the thing that's going over the web, yeah? And this service would be like this would be the hotel service, in my example. So the hotel service is updating its own database.
Okay.
So we're doing JTA within the same organisation. So the point here is we're never doing JTA between organisations.
Yeah.
You're always doing it locally.
But when you are going over the web like that, your relationship with the person you're talking to is still kind of transactional.
But compensation based.
So it's,
So the idea is you're kind of splitting it up into lots of quick JTA transactions that are fully in control of that domain. So it's lots of, essentially you've got lots of small pieces of work rather than fewer larger pieces of work which you have to wait for other parties before you can finish them. It's like, if you've been given a series of tasks, you like the tasks that you can start and finish and cross off the list. You don't like tasks.
Concrete details that I haven't quite got my head around, but that's not.
Okay.
I'm trying to fix it now.
There is I've actually got there's a design discussion on how to do this wiring up, where we talk about the specifics, if that interests you. I'm trying to think if you Google for WSBA bridging, if you Google for that, then you should get a discussion of what needs to be done to tie those two things up. But I think I can. Yeah, I think it might be easy to have a look at that. I'm not sure if I can explain it succinctly enough to. Essentially, the idea is that you don't commit the JTA transaction until you've got a log of the compensation handler, and then the transaction manager can figure out, if it's got one but not the other, what the scenarios are. It's that's what the transaction manager is good at, understanding all these corner cases. So it's an already kind of solved problem.
So you use ACID locally, but not from the distributed point further out. That's kind of what you're saying, right? You break it into a bunch of littler ACID transactions. But there one thing I was looking at, so when you say that changes are visible.
Yeah.
So what if I would have thought that you wouldn't actually commit, like you would come back with a second signal to your for the local ACID transaction to commit later on. But when you're saying the changes are visible there, that would mean that other applications could then use that data, which may be then compensated, and then that creates problems.
Yes, so that's the thing. You have relaxed isolation and consistency, so that is something to be aware of. But as I was saying in the example with the booking, because you can potentially mark it as pending here in the database, even though that it's visible that the thing was pending.
Oh, okay.
It doesn't necessarily matter, because at this point all you see is that I've got say 10 bookings that are made, and I've got 3 pending ones, because you see the one that was marked as pending here.
Okay.
And then in the next database update here, you then change the state from pending to confirmed, or if it's compensation handler, then you change it from pending to cancelled or whichever. But, so what you kind of do is you're trading off, in this case, in the ACID case you have one JTA transaction with kind of a small amount of logging. You're trading it off for 2 separate JTA transactions with twice the logging, plus the logging of the confirmation handler and the compensation handler and any state required at this point. So it doesn't come cheap, but the important thing is you're not having to, you can complete your tasks. You get given a task and you can complete it as quickly as you can. So these are like short-lived, completable tasks. So I was giving the analogy before, it's nice when you've got on your to-do list, you've got some tasks that you can start and finish without interruption. It's not nice when you've got a task that you have to start, do some work and then wait on somebody else. And then when they come back to you, then you can finish the task. And you potentially have to kind of in that analogy, you might have to lock some resources in the meantime, you don't know what's happening. You're waiting on this other person to tell you what the outcome is. I guess kind of like a good example is kind of like trying to book a night out. Somebody might ring you up and say, do you want to come out on Friday? You're like, yeah, great, sounds good. And they say, but I don't know for sure whether we're going out. You'll have to wait until I've rang everybody else. And at which point you can't go out on Friday. Well, you could do, but they'd be a bit annoyed with you if you did. But your Friday is essentially booked, or out. And then you're waiting for them to come back to you. At which point you know whether you're going out or not.
Let's make an example of that.
Pardon?
Let's use that for your example.
Yeah, possibly.
And you've got you can use it to illustrate the alternatives, right? Because if one person then does agree to do something else on their Friday, then you find someone else to ring, like, well, who's going to try it?
That's true. Yeah, that's true. You find, if you didn't really like, you're not that bothered about that person. Well, you kind of get situations where you've got a friend that you haven't seen in ages, and they're like the hotel booking, you really want them to be able to make it. And then you've got loads of other friends that you see every week, but it would be nice for them to make it. But if only one of them could make it, then you might think, oh, let's find a time that everyone can make. So there is kind of the analogies there. And the ones that you've already told you can make are coming, you might have to ring back and say, actually it's off. And then start again with another night or something. Yes?
I'm unclear what it does behind the scenes for WSBA. In your simpler booking example, for instance, you had a database and web services, but then in your compensation confirmation handler, you only dealt with the database. So is there some magic behind the scenes that compensates for the web service calls?
Yeah, so what happens is when you invoke business logic, so here, so this is a web service call here, yeah? This invoke thing would be a web service call in that example. We begin a compensation-based transaction which is associated with the thread. So anything that runs on that thread can look and find out the current transaction. We then have an interceptor here, which is kind of always there. It looks for this thing on the thread as context, and if it's there, it serializes the context and puts it into the payload of the message. That comes across here, and there's another intercept here that's looking for these. And if it sees a transaction context, a compensating transaction context that is, it will then say, okay, I need to enlist in that existing transaction. So then actually makes a call to the transaction manager to say that I'm kind of involved in this transaction, I want to be notified of what's happening.
That's part of the WSBA protocol.
Yeah. So at that point we're in WSBA. And then the middleware then associates the thread with that transaction. So it's the same as what we had here. There was a compensation-based transaction that was associated with the thread here, and then there's now one associated here. So at that point, when we begin the JTA transaction, because the middleware knows about both, it's capable of, this is what we haven't got quite now, but it's capable of tying the two together. So what it essentially will do is it will begin a new JTA transaction here, which is called a transactional annotation. When we update the database, that database is enlisted with the JTA transaction, and then what happens is that that returns here, and then when this service says it's finished, which is done by the interceptor, the transaction manager will then prepare this database. So at that point the database can either be committed or rolled back. It then logs its compensation handler for undoing that work if needs be. And once that's logged, it can then commit this database. So it does it in the right order. I think this is the specifics of it. And then, so you've potentially got a small window there where you've logged the confirmation handler, but you haven't committed the transaction. If there's a failure there, what would happen is that this would be rolled back, but the confirmation handler would already be written. And then when the transaction manager comes back up, it will call compensate, because we never got far enough in the transaction to confirm it, and the other parties didn't get to them yet. So it will invoke a compensation handler for something that didn't actually happen. But as I was saying before, this needs to be idempotent anyway for the reliability to work, because this confirmation or the compensation handler is re-invoked until it completes successfully. Because you can get a failure when that's invoked as well. It's not enough to just begin the call, you have to actually go through with it. So at the moment it has to be idempotent. So you have to code your logic in a way that you check, was this work already compensated? So again, it's application specific. So does that, have we got another question, or does that answer?
Well, I think I'm still not clear. Who writes the compensation handler for my web service, for my hotel booking web service?
The hotel. The same person who wrote this service here. So the person who writes the, I'm writing a make booking method that's invoked by a web service that goes and updates a database. The person who wrote that logic would typically write the compensation. Now, one thing you can do, but it's not as reliable, is that you can treat the service as a non-transactional resource, which is probably what you'd have to do at the moment, I guess, if you want to include something like, and I think Expedia or somebody, if they had a web service interface for making bookings, you'd have to treat them maybe as a one-phase resource. So you would essentially you'd have to write this bit here would be in would be the client. And then instead of invoking the database, you would invoke Expedia to make the booking. And then in the compensate method, in your logic, you would then make a remote call to Expedia to say, oh, actually, I don't want that booking anymore. And providing Expedia allows you to cancel within 20, I know sometimes they say you can cancel within 24 hours of the date of the booking. So that compensation handler would check the date, check it can compensate, cancel it. If it can't, it would have to somehow notify the application that it didn't happen, or it would have to take the hit on maybe only get 50% back or something. So you can kind of wrap, the same way you can wrap a printer or an email client, you could also wrap a remote service. And it doesn't have to be a web service either, because you're not trying to, it could be a REST service, which maybe is more common nowadays, because you're not trying to propagate this transaction context. So we tie to web services because that's the only technology we've got at the moment for propagating transaction context. But we could use REST, for example.
I wanted to ask about deployment. Do you see Transaction Manager as a separate process of your server, or do you see it being embedded inside the client or somewhere else?
So in theory, it can live anywhere. So the client, this Transaction Manager could live with the service. So the client could call begin, make a remote call to begin the transaction on the service, or it could live with the client, or it could be a third party. So it would depend kind of on it's an architectural decision basically.
From your implementation point of view, how do you plan to implement?
It's already implemented and it can be anywhere. So what in the client, in Jboss or Wildfly, in the client you've got a configuration option, which is the URL of the coordinator. So the transaction manager is called the coordinator in web service transactions. And basically that server then will always, unfortunately, for all applications, go and use that particular transaction manager. So you can, and that could be, it defaults to localhost, so it defaults to the local one in the local server, but you can tell it to go and use a third party one or the one that lives with one of the participants. So because it's web services, they're all web service endpoints, it doesn't really matter where you place them. And the protocol kind of talks web services, so they can kind of, in theory, you can place anything where you want. So it's kind of up to the architect really to decide how to put things. I think in your example you're saying that because you're writing to a local log, and the clients may be kind of lightweight, or they may be in memory or something. You might want to use a reliable service. You could use a reliable. So okay, so this could be an unreliable client. You could have lots of these. Running on unreliable hardware, which is fine. If they fail, then it doesn't matter. In our protocol, it doesn't matter. The transaction manager does need to be reliable because it's storing logs, as you say. So in that case, you wouldn't want to store it on here. So maybe you would have one or more reliable nodes where the transaction manager runs, and then lots of unreliable but many clients. So that would work. And then your service again, that would need to be. That would need to be reliable too, because it needs to log the compensation handler. So this service would need to be on reliable hardware as well. When I say reliable, I mean kind of you can rely on the disk writes. So you can write something to disk, and then if the machine fails when it comes back, you'll see it again. It'll still be there.
So in a sense, it makes sense to call it a transaction manager and the service. If the service is coordinating compensation context.
Yeah, you could, but one of the problems would be because the transaction manager is doing the coordinating, he needs to be able to see the services. It also needs to be able to see the client as well, which is a kind of flaw in the protocol, because there's an asynchronous communication between the client and the transaction manager. So the client sends a message to the transaction manager, and then it waits for an asynchronous response, which is great because it means that we don't have socket timeouts. But it's not so good in the fact that if this is firewalled or natted, it's difficult for the transaction manager to talk back to it. So this transaction manager needs to see everybody. The client needs to be able to see the service. The service doesn't need to be able to see the client. And this guy needs to be reliable, and this guy needs to be reliable. But this guy doesn't need to be reliable. So the only problem with the client not being reliable is you can request the transaction to be either closed or cancelled, but if it fails here, then he won't actually find out what happened. There's not an easy way for him to find out.
Basically, with databases, usually transaction manager, if client dies,
yeah,
transaction manager will wait for a certain period of time and then roll the transaction.
It will what, sorry, for a certain period of time?
Say if you use Oracle database, right?
Yeah.
And then you have client writing to database.
Yeah.
And client is doing two-phase commit.
Yeah.
And the first phase is successful, and second phase is unsuccessful because client died.
Yeah.
Doesn't disconnect.
Has the client told the transaction manager to commit at that point?
Yeah, first phase was successful.
Okay, the first phase was
Second phase timed out.
Yep.
So transaction manager on server side typically applies some heuristics and it decides should it commit or should it roll back.
Yeah.
So it's pretty much the same situation here.
Yeah.
So transaction manager should apply some heuristics if the client died and be able to automatically compensate for this transaction maybe.
Yeah, so at the point when the client tells the transaction manager what to do, the client's kind of...
Yeah, the client can die in between.
Yeah, the transaction manager then, at this point in this case, because we've already got work that's done, it's already been persisted, so the transaction manager, assuming that all that work's been successful, it will then go and close, you'll then go and, you know, confirm all the work. But whereas in a two-phase commit protocol, if you've got, so...
Well, according to the previous slide, you suggest two-phase approach still. It just semantics of each phase are different.
Yeah, it's still a two-phase protocol, and under the covers, it's kind of implemented. It's because we've got Arduino core at the centre, which is kind of that protocol engine, which has been, you know, it's been around for, you know, over 20 years, and that's kind of it can run general transaction protocols, and this is kind of the compensation-based transaction is kind of like a subclass of one of those. So it's kind of already it is a two-phase protocol basically. So it's already kind of extending the work that's already been done. So we're kind of getting all the kinks have been ironed out of it before this was implemented. Do you see what I mean? So yes, it is a. So yes, the short answer is that yes, it is a two-phase protocol, and it kind of behaves in the same way, but the semantics are different in what happens in each phase. Plus, there's the additional thing of serializing the handlers and the data. Yeah, Richard?
Yeah, it's sort of been implicit in your discussion that you've been using ACID transactions, but ACID transactions with pessimistic locking. There's another approach with optimistic locking. And I'm just curious how an ACID transaction approach with optimistic locking, where you don't take locks as you modify data items, but just check for locking conflicts at the end of the transaction, how that compares with the scheme presented here.
Yeah, so it's better if so this diagram kind of covered that. So we're saying here with pessimistic locking, you acquire the locks as soon as the business logic uses the data. With pessimistic locking, you acquire it at the prepare phase. So it's better in that the window is smaller, but you still have the problem where you have to wait while all the other resources are being prepared. Because you're still holding the locks whilst other parties are doing their business while they're being prepared. So you've still got this locking window, although it is smaller, and it's not under the control of the client anymore.
Once you start the commit, that's when you still got a problem with optimistic locking.
Yeah, so you see the locking window here is from when the prepare happens until the commit or rollback occurs. So we've got a dotted line here to show that kind of the database is kind of waiting. It's not been involved. So it's better. But remember, that's only going to work if you've got a write frequently situation, then you can't really use optimistic locking because it's regularly going to notice that things have changed. So it's not. But I think this is kind of the common, optimistic locking is kind of the common, my understanding is that this is the common scenario anyway, rather than pessimistic. So we easily say you've still got this window here.